Greetings and welcome to lecture number 6 in the series of lectures about the ergodic decomposition. In the last lecture we finished the discussion about the ergodic decomposition, and we discussed in particular unique ergodicity, which is the situation when a dynamical system on a compact metric space has a unique probability measure that it preserves. Today we will talk about application of that is due to Hillel-Furstenberg. Now, at the time that this lecture is being recorded, in April of 2020, it's been about 3 or 4 weeks, I think, since it's been announced that Margulis and Furstenberg will win jointly the 2020 Abel Prize for their achievements in mathematics. The reason Hillel-Furstenberg won was primarily his extremely imaginative and, in my opinion, also very surprising applications of ergodic theory to combinatorial number theory. The most important, the most famous at least application is a proof of Semeredi's theorem, which he gave only a couple of years after Semeredi himself proved the theorem. And we will discuss in the next lecture, which is not a part of this series of lectures, but will be the next series of lectures. Today we will discuss another application that Hillel-Furstenberg gave to ergodic theory to proof in combinatorial number theory. In the beginning of the course, we covered a section titled Before Ergodicity. In that section, we discussed a theorem which I think is quite important and influential of Hermann Weyl, which said that the orbit of a point under an irrational rotation in the circle is equidistributed. It's quite easy to see that the orbit of every point under an irrational rotation is dense in the circle, but equidistributed is a much stronger condition. So let's review what that condition is. This expression here is what we need to now parse. The part in red here, alpha n plus beta, is the orbit of a point under a linear map on the real numbers. Alpha and beta are at first any real numbers, although in order to make the rotation irrational, we will of course have to insist that alpha is not rational. Beta can be rational, beta can even be 0. Now, what we see here is the exponential of 2 pi I times the red part, which is the orbit of the linear function, or affine function if you want to be more precise. We take the first capital N points of this orbit. The exponential map sends it, of course, into the circle, and we count the number of points of this orbit that land in an interval. Now remember that an interval in the circle is just what we think of as an interval. It can be either open, closed, or half open, half closed. That doesn't matter. We take 2 points on the circle, and we take all the points between them, either on one side or the other. So 2 points on the circle define 2 different intervals. We ignore the question of open and closed because that's just about the 2 endpoints themselves. Equidistributed means that the number of points from the orbit that land inside the interval is the right number. If the interval is short, it's very few. If the interval is long, it's very many. In other words, look at the number of points from the orbit that land in the interval, divide by the total number of points n, and the limit as n goes to infinity needs to exist and equal the length of the interval. That would be equidistributed. And you will recall maybe from the time that we discussed this was before we started discussing ergodicity and the ergodic theorem and all that. This was a special property of intervals. It is certainly not true if you replace interval with a measurable set. Now, what are these points in the interval? If we start with n equals 0, we simply get the point which is the exponential of 2 pi I times whatever the number beta is. That's a certain point in the circle. And every time we apply n equals 1, 2, 3, and so on, we multiply this point by the point x 2 pi I times alpha. In other words, we are rotating the circle by amount exponential of 2 pi I times alpha, and we're looking at the orbit of this particular point x 2 pi I times beta. And Weyl's theorem says that for whatever beta is, in other words, the orbit of whatever point you want to, this will be equidistributed as long as the rotation is irrational. This is the condition here, that alpha is not in Q. But in fact, Weyl proved a much more general theorem than that. Weyl actually proved this theorem for almost any polynomial Pn which will replace alpha n plus beta. Alpha n plus beta will just be the case of a polynomial of degree 1. If I say any polynomial, you already know it's wrong, because even in degree 1 we have to insist that alpha is irrational. So you get something like this. This is the exact same expression that we had in the previous slide, except that here we replace alpha n plus beta with Pn, the value of some unknown polynomial. If you want this to be equidistributed, this is the condition for equidistributivity, then you know you need to insist on something. What you need to insist in the case of linear or affine function is that alpha is irrational. In here, you need to insist on something similar. One of the coefficient of p needs to be irrational, and it's not the coefficient alpha 0. Alpha 0 corresponds to beta here, and that will not help us. And our goal today is to give the details of the setup for the proof that Furstenberg gave to this. In 1960, Furstenberg discovered a proof of this that uses, in fact, the concept of unique ergodicity. We will today construct a lot of uniquely ergodic systems, something called skew product. We will relate those systems to equidistributivity, and we will sort of find the orbit of the polynomial in a specific one of these skew products and deduce from that unique ergodicity. That's quite a lot of work for one lecture, and what I want to really concentrate on is the setup, how we construct this uniquely ergodic system, how we know that they are uniquely ergodic, and to bring you all to the situation that deducing equidistributivity is rather mundane. Some of the details are just multiplying matrices and stuff that I believe any of you can do. I say I believe any of you can do because this will be on YouTube and I don't really know who is going to be listening to this. I did want to recommend one book above all others. Furstenberg's book, Recurrence in Ergodic Theory and Combinatorial Number 3, is wonderful. It has extremely interesting information. This is only a small part of it. It's very beautifully written. It's been reissued recently by Princeton University Press in their Legacy series, which is reasonably priced too, at least for a professional math book. I think it's something like $36 right now. Another book that I've used a lot is Einsiedler's and Ward's book, Ergodic Theory with a View Towards Number Theory. A lot of this lecture today is taken out of that book, and it's a very, I find it to be a very well-written and useful book as well. And of course, there are many other books that cover this and similar material. Now, let's remember what our setup is. We're talking about XD, which is a compact metric space. We will fix actually a specific probability measure preserving system that's based on X. X will be the compact metric space, Bx will be the Borel sigma algebra on it, mu x will be a specific probability on Bx, mu x will be a probability on Bx, and T will be our measure preserving transformation. Now, in addition to that, we will look at S1, the circle in C, which is of course a group under multiplication with the Lebesgue or Haar measure, which is normalized to have total measure 1 to be a probability measure. As a matter of fact, you can use absolutely any compact metric group with the Haar measure. But in this, for our lecture, we only need S1, and to simplify notation, we'll stick with S1. Now, here's a new ingredient. We need phi, which is a function from our compact metric space X into S, and phi needs to be continuous. And the skew product now is going to be called Y. It's X cross S1 with the product metric. What makes it skew is the way we act on it, which we will describe momentarily. Now, of course, Y is also a compact metric space, which of course means that the space Cy, the space of continuous function Y, is a separable space. Now, the new ingredient is the action S. S is a function, a continuous function from x cross S1 to x cross S1, and it's given as follows. On the first coordinate S, x, which is just a point of capital X, we act exactly the way we acted before by applying t. On the second coordinate t, we act by multiplying by phi of x. So remember, phi of x was a function from x to S1. So phi of x itself is a point in S1, and you can multiply 2 points in S1 or more generally in any other group. If you are talking about any other group, which may not be abelian, then it's actually important to insist that phi of x is to the left of t. So here is the theorem that Furstenberg proved. First of all, S is measure preserving. If S is ergodic, then it is uniquely ergodic. And this is a very important concept for us today, so let's remember what it means. It means the following. If this transformation S is ergodic, then there is no other measure on Y that will make S, will be preserved under S. In other words, the space of all probability measures that are preserved under S, what we called MT in the previous lectures, is exactly the same as the space of all extremal probability measures, which you'll recall are the ergodic ones, which is a single measure. We will discuss the theorem of this proof shortly, except this part here about measure preserving. Measure preserving is a pretty simple calculation, so we'll skip that one. Now, before we get into the discussion of the proof, let's talk a little bit about equidistributions. When we talked about equidistributivity on the circle, we used intervals. This is not super convenient, so let's give an alternate definition of what equidistributivity here. A point x in y will be called equidistributed, with respect to a given measure mu sub y, if the following condition holds. For all continuous function f, the limit, the ergodic limit of, which is the limit as n going to infinity of the average of the value of y on the head of the orbit of x, simply equals the total integral of the continuous function. So there's an obvious exercise here, because for the case of S1, we have two different definitions of equidistributivity, and you need to show that the two agree. One thing which is interesting is that when we discussed equidistributivity in S1, we said we must insist that we talk about intervals, because the theorem is false if we allow all measurable sets. This is reflected in the new definition because we insist that we talk about continuous functions. If we replace this with all measurable functions, well, we need to take an integral here. You can take L infinity, L2, L1, whatever you want. Let's take L infinity. If you replace continuous functions with all bounded measurable functions, this definition will make no sense, and the theorem that we want to prove will be false. Another exercise is, and this will play a key role later on, is to show the following. If you have a single point which is equidistributed with respect to two different measures, mu1 and mu2, then the two measures are the same. Over here, of course, it means that mu1 and mu2 will have the same integral, because the integral will be given for any function f by the ergodic average. So this exercise is actually something that we know, and I do want to discuss it because it's very important moving forward in today's lecture. This exercise actually just amounts to showing that a measure, mu1 and mu2, is determined by the value of integrals of continuous functions. So this pretty much does the exercise for you. The following proposition is very important, so we'll give it a name, proposition star, and it's also, I think, interesting in its own right. If the measure μi is ergodic, then almost every point is equidistributed. So let us start with proving this proposition. So recall that Cy, the space of continuous function of y, is separable, and therefore we can fix some countable set f sub I of continuous functions which are dense in Fy. Now, for a fixed I, we can apply the Birkhoff's ergodic theorem and conclude that there exists a measurable set E sub I satisfying the following two conditions. First, it's essentially the entire space. In other words, the measure of the set is 1. And second, for any x in this set, the ergodic average converges to the integral of the function. So recall that Birkhoff's ergodic theorem says that for almost all x, in other words, there exists a set E1 of full measure 1, and for any x in that set, this ergodic average converges to some function, we call it f star, which is measurable and invariant under S. But if mu sub y is ergodic, there are no non-constant invariant functions, and therefore the function that you get here must be constant, and the constant that you get has to be this one. Now, this is just for a single I. Take the intersection of all these EIs, of course, because we're intersecting sets of measure 1, we get a set of measure 1 as well. On this set, we have this condition holding for every one of our FIs in this set. And then, and the details here are again left as an exercise, because this set Fi is dense, we get that every x in here is actually equidistributed. What we get is that every x in here satisfies this condition for Fi. You need to use density of Fi and Cy to see that every x in this set, the intersection of the AIs, satisfies this condition for any f in C sub y, which is our definition of equidistribution. This proves proposition star. Now, I'm tempted to say, let's take this intersection as our set E. There is a little bit of a problem with that because we don't know exactly what these sets E sub I are. We do know up to set of measure 0, which in a sense is all we care about, but we don't know exactly. So I want to set the set E to be all the equidistributed points. It will contain, of course, this intersection, and therefore we'll have measure 1. This is a little bit cheating, and I have to admit this now, so let's deal with this once and for all. I don't know that E is measurable. I do know that it's contained in the space which has measure 1, and it contains the intersection of EI that also has measure 1. So one way out of this is replacing, both in X and in Y, the Borel sigma algebra with their completions. So in S1, you know, with the standard Lebesgue measures, it will be replacing the Borel sigma algebra with the Lebesgue sigma algebra. At any rate, this technicality is really not in the heart of what we're doing. So let's agree that we accept this set E as our set of measure 1 moving forward, and maybe we needed to complete the measure for that. Now, here is the key property of this set E. The set E is invariant. Now, invariant under what? The set E is a subset of Y, and S1, the circle, acts on Y. So let's use some notation for that. For any pot theta in S1, we can define a function f sub theta, a continuous function in C of Y, which is simply defined by rotating the second coordinate by amount theta. You can apply this, as we said earlier, for other groups, and other groups may not be commutative, which is why we're putting theta on the right. And so to see that the set E is invariant under this action, we pick a point xt in E and some f continuous on Y, and then we have the ergodic limit of f applied to x t theta equals, the red equal will be justified momentarily, the ergodic limit of, see here is the ergodic limit because we're applying our transformation, of f theta followed by f. Well, we know that this equals the integral because xt is in E, which means xt is equidistributed. This is exactly the definition of equidistributed. And in terms, this equals the integral of f, the blue equal sign. It's quite simple, but we'll justify it also in a second. Now, why do we have that the red equal sign holds? This is simply by associativity. Look at the point that we plug in here. This is Si of x t theta. Si of x t theta, Si by definition applies t to the I to the first, by Si I meant of course s to the I, applies ti times to the first coordinate and multiplies the second coordinate on the left by cxi time. Well, this is simply a certain point with the second coordinate multiplied by theta on the right. That's just f theta applied to this coordinate. And so if you look at what you're left with here, it's x with t applied I times and t with cx multiplied I time. That's by definition si of xt. And this is what we have here, si of xt with fi acting on it. That justifies this equal sign. To justify the blue equal sign, simply notice that f theta by construction preserves measure. And so this completes the proof that E is invariant under S1. If you have any theta in x1 and xt in E, then x t theta is also in E. So let's go back to complete the proof, and maybe we need to remember what proof we are trying to complete. We are trying to prove that if mu y rather is the only ergodic measure, excuse me, it looks like I really do need to remember what I'm trying to prove. We're trying to prove that if the measure that we have on y, mu y, is ergodic, then it's uniquely ergodic. Okay, so what we have seen so far is that the set of equidistributed point E has the form of E sub x cross S1. Any set that's invariant under the x1 action has this form for some measurable set mu in x. Of course, mu x of Ex will have to have measure 1 because otherwise E will not have measure 1 in Y. Now, what we set out to prove is the unique ergodicity. To that end, let's take another invariant measure mu, another ergodic measure mu, and see that mu in fact does have to equal exactly, that nu has to equal mu. We can take our set nu, our measure nu on y, and push it forward to get a measure nu sub x on x, which will be invariant under T. Of course, on x we do have unique ergodicity. That was the assumption of the theorem, and so mu sub x must equal mu sub x, and with that we get that nu of E, which simply equal mu or x of E sub x, equals mu of x of E sub x equals 1. Both nu of E and mu of E are 1. The upshot of this discussion is since by proposition star we know that every point of y is almost every point of mu equidistributed and nu equidistributed, we now can find a point that is both mu and nu equidistributed. And for a point like that, we get that for any continuous function, the integral of f d mu equals the integral of f d nu. This is simply because this integral here on the left is the ergodic average of the orbit of the point xt, and this here on the right is also the ergodic average of this point under S. They're both the ergodic average of the limit of the ergodic average of this point under S, and the ergodic average does not care which of the two measures you're using. Anyway, the upshot of all this is that both nu and mu give the exact same value of integral for every continuous function, and since we know by the Riesz representation theorem that the value of a function on the value of integral on all continuous functions determines the measure, we conclude that mu and mu are the same measure. And of course, this is exactly unique ergodicity, so we have done most of the work that we needed to do today, which is construct uniquely ergodic systems. In order to get the application that we are after, Weyl's equidistributivity, let us consider the following transformation S from the k torus to the k torus. Of course, the k torus is the product of k circles. The transformation is given here in terms of what happens from rk to rk, where the k torus is given as always by modding out by the integer lattice z to the k. The first coordinate simply maps x1 gets mapped to x1 plus some unknown number a. This, by the very first Weyl equidistributivity theorem that we proved a long time ago, is equidistributed exactly when a is irrational. And the remaining coordinates simply get mapped. x2 gets mapped to x1 plus x2, and so on all the way till xk gets mapped to xk minus 1 plus xk. If it is actually the case that a is irrational, then we know that the first coordinate defines an irrational rotation on S1, and then a repeated application of the Furstenberg's theorem tells us that the whole thing is uniquely ergodic on the torus. Once we know this, in particular we get that this action is uniquely ergodic on the last factor. Now it's a linear algebra exercise, essentially multiplying matrices, to see that what happens on this last factor is given by this formula right here, where these are of course the binomial coefficients. This is a formula given in terms of variables x1 through xk, or more precisely a, x1 through xk, but if we change our perspective, given a and the value for x1 through xk, this formula is a polynomial in n. The highest degree that appears only here, and so on for lower degrees. And the exercise is to show that there is a choice of a, x1 through xk, so this as a polynomial in n is exactly the polynomial that we started with, and from this exercise, from this fact, deduce Weyl equidistributivity theorem. So I will leave this for you, but just a little afterthought here. It seems strange, perhaps a priori, that equidistributivity will be related at all to unique ergodicity. Should we expect such a thing to hold? Equidistributivity, by definition, was given in terms of integrals. Now, let's consider the measure delta x, the atomic measure centered at x, which simply gives measure 1 to any set containing x and measure 0 to any set not containing x. The integral of any function d delta x is just the value of the function at x. So now, if we take mu n to be the average of the translates of this function, we know that, just from this fact over here, that the integral of f d mu n is the ergodic average of the function f on the orbit of x. Weak compactness tells us that there is some convergent subsequence of these measures to some measure mu. If it is uniquely ergodic, because mu has to be an invariant measure, if the transformation is uniquely ergodic, then mu is in fact the unique ergodic measure. And therefore what we get is that on this subsequence, the ergodic average, which equals the value of the function, converges to the integral of the function d mu, the unique ergodic measure, which exactly is the definition of equidistributivity. So we see that if there is a unique ergodicity, every single point is in fact equidistributed. So in hindsight, it is actually not particularly surprising that equidistributivity is very closely related to unique ergodicity. Well, this concludes what we had to say today. I hope I was able to show you the creativity in Furstenberg's application of ergodic theory to a combinatorial theorem which a priori maybe seems unrelated to ergodic theory, although in hindsight, as we can see on the slide right here, it is very closely related to it. I hope you enjoyed it. Next time, which I'll try to get done as soon as I can, we will talk about Furstenberg's correspondence theorem, which is really one of the most beautiful things, I think, in mathematics, and I hope I'll be able to produce a lecture that will show you how nice it really is. Until then, watch this again if you need to, send me all the questions that you have, and I'll see you next time.